Hello and welcome back to my channel to the ConQuiz series 15. Today concept booster on quantum part 3. The topic that we'll try to cover today, quantum postulate, particularly postulate number 2, Hermitian operator, bra-ket notation and definition and properties of Hermitian operator in bra-ket notation. Then an interesting line, if I were not there, quantum mechanics would have been impossible. Then anti-Commutator and anti-Hermitian and a few related problems. So let us start with quantum postulate. So in the early 1930s, actually quantum mechanics was formulated in terms of postulates, and 6 postulates are there in total. But what does it mean, postulate? It's a claim or assumption of truth, especially as a basis for reasoning. A postulate cannot be proven, but it can be tested by experiments. And so far, no conflict has been found of any of the postulates with experiment or experimental results. So that is postulate, but I would not discuss one by one all the postulates here today. Rather, we will start with postulate 2. To every observable in classical mechanics, there corresponds a linear operator in quantum mechanics. So what linear operator means, that we have discussed in the earlier video, ConQuiz-15. Here postulate 2 is slightly modified to give another version. To every observable in classical mechanics, there corresponds a linear and Hermitian operator in quantum mechanics. So all the same, only the word Hermitian is added in the next version. Well, let us have a problem for linearity, and then we will go for Hermitian. Prove that if psi x is a solution to the Schrodinger equation, then any constant times psi x also a solution. So it's rather simple. If H is a linear operator, then we know that H C psi x is C H psi x. Okay. So the constants comes out of so C is any arbitrary constant, and psi x is the eigenfunction of H. So C E psi, H psi is E psi, and since C is a constant, we can take it here. So E C psi x, because E is a number, C is a number, so we can write the last step anytime. But in the first case, since H is linear, we can write H C psi is C H psi. That is the point. So clearly, we see that C psi acts as an eigenfunction with an eigenvalue E, the same eigenvalue. So H C psi is E C psi. Okay. So C psi is also a constant and is also a solution. Okay. But our focus is not linearity, but Hermitian operator. Okay. And it demands that a quantum mechanical operator has to be Hermitian, right? Why so? So let us first see what do we mean by Hermitian operator. Let us start with an eigenvalue eigenfunction equation. A psi is A psi, right? A small a is the eigenvalue. Now here the operator in general, A hat, and the function psi may be complex, but A, since it's an eigenvalue, that means it is the value of a measurable or observable quantity, so it must be real. So we can say that A, small a, has to be real. Okay. So starting from this eigenvalue eigenfunction equation, what we can do, we can multiply this equation both sides, left multiply by psi star and then integrate. So you get psi star A psi is equal to A psi star psi. A is a constant, so comes out of integration, but psi star psi is nothing but the normalization condition, so it gives 1. So the final result is A. So psi star A psi dx is A. Suppose this is equation number 1, and now what we do, we take the complex conjugate of this equation, of both sides of this equation. So A star psi star is A small a star psi star, right? But assuming that A has to be real, so A star can be written as A. So this is the final equation. Now what we will do, we will left multiply again both sides of this equation by psi and integrate. So what we get, psi A star psi star dx is A psi star multiplied by psi and integrated. So A psi star dx, and again psi star dx integration is 1, so it is again A. So this equation number 2 suppose. So from 1 and 2 we see that the result is finally both A, but the left hand side then must be equal. That means we get this left hand side is equal to the left hand side of this equation. So that we can write in this way, that psi star A psi, this means this one, equal to psi A star psi star. So this equality we are getting by imposing the condition that A has to be real, or in other words, if A is real, then this follows this condition. Okay. Actually, a bit more general way to write it, that F star AF is F A star F star dx. So as if you are taking this psi or F towards left and this psi star or F star towards right, towards right. And more generally, what we can say, that F m star A F n, so they are two different functions, right, is equal to F n A star F m star. That means this F n as if it comes towards left and F m star goes towards right. So this is the general or most general condition for A to be real, right. So this is what we mean by Hermitian operator, right. Now we are going to introduce a new and very precise and compact and easy to use notation. We call it Dirac's bra-ket notation. Let us see how it looks like. So this is the definition of Hermitian operator in integration form, Fm A Fn and now Fn A star Fm star. Now we are trying to get the Dirac notation, bra-ket notation. So this is called the bra-ket notation. Actually this part, left hand side part, is called bra and this part is ket, and usually the operator is enclosed within two vertical lines. Sometimes the right vertical lines we omit, but this is the convention usually. And what does it mean? If it equates with the integrated form, then we see that in the bra m, that means Fm, actually it is here in Fm star as Fm star, and on the right ket position An is as such a Fm. So that means whatever in here, whatever is with a star can be written in the left side bra position, and otherwise it goes to the ket position. So that is the usual way of bra-ket notation. Now the right hand side, okay. So Fn A star Fm star, Fn A star Fm star. Now you know that a function fx, if you take the complex conjugate 2 times consecutive times, that means fx star, then again star, it leaves you the original function fx, okay. So that advantage you are taking here in this step, Fn is converted to Fm star. I am taking a complex conjugate. A star becomes A and Fm star becomes Fm. So we have taken complex conjugate of the whole thing, and if I take again the whole thing is bracketed and take star, that is second time the complex conjugation, that means it leaves the original left hand side as such unchanged. So that we can do star and then again star to leave unchanged, something unchanged. But in bracket notation, as I have mentioned, that Fn is with star, so it comes here in the bra position, and AFM without star, so it comes here in the ket position, and the whole thing is star is there, so the star is there. Okay, so A is Hermitian operator if this is equal to that in the very first line. So left hand side of this is equal to this. That means in bracket notation MAN is equal to NAM star. So this is also called turnover rule, because there is really a turnover. M and N have exchanged their position, N and M, and with an extra star has arisen here. So MAN is NAM star. And more conveniently, we can write this is not clear. Okay, follow my words. That NAM, so N in the bra position, that means actually Fn star, and a star is there. So Fn star star means Fn. So you can take it in the ket position, and AM star, so you can take it in the bra position. So that means the final, this is equal to AM in bra and N in ket. So as if you are taking A from the middle position to the left. So AM N, if it is equal to MAN. I repeat, if MAN is equal to NAM star, or in other words, if MAN is equal to AMN, then A operator is Hermitian operator. Okay. So the next slide, it's all about the property of Hermitian operator, and it says that the eigenfunctions of Hermitian operators are orthogonal, right? So we know what orthogonal means. Let us see what it tells, how it can be proved. Suppose two eigenvalue equations, A psi n and A psi m. With the first one, what we do, we left multiply by psi m star, and then A psi n is A n psi m star psi n, right? So in bracket notation, what would it looks like? It look like psi m with star, so in bra m, and then A psi n, so in ket position A psi n means A n, and on the right A n outside the integration, then m n in bra position m and then ket n, because psi m star is here, comes in the bra position. So what you see that MAN is AN MN. Okay, this is the first equation. Now the second equation, what we do, we take the complex conjugate of the second starting equation, A psi m, AM psi m, and we take the complex conjugate, that means we get A star psi m star. Okay, now we left multiply by psi n, psi n. In the first case we left multiplied by psi m star, but in the second case we are taking the star first and multiplying by psi n, so psi n. And again we use the same trick, that we take the complex conjugate of all the terms here, so psi n becomes psi n star, A star becomes A, and psi m star becomes psi m. But again, to leave the original unchanged, we take another star here. Okay, so if you write this one, so psi n star star, so that is psi n, and psi m star. So psi m star, and A psi m is actually am psi m. So am psi m star. So am star comes out of integration. So we get finally am star psi n psi m star. Okay. So in bra-ket notation, again we see that this is equal to am star n psi m star, that means m in bra, n in ket, right? And the left hand side comes from here, psi n with star, so n is in bra, and am psi m, so am is in ket, and the whole star is there, so star is there. Okay. So I repeat that from this equation, left multiplying by psi m star and integrating, we get this result. And with this equation, first take the complex conjugation of both sides and then left multiply by psi n and then integrate to get this result. Okay. Now what we do? We subtract this from that. So MAN minus NAM star, and on your right we get AN MN minus AM star MN. So this is the final result of the subtraction. So let me write it again in this slide. And interestingly, you see that I have whatever I have done it deliberately to get the advantage of the definition of Hermitian operator. Because if A is Hermitian, then you see the turnover rule, Mn have changed their position, Nm with a star. So actually this part is 0 if of course A is Hermitian. So we can say that the left hand side is 0 is our operator is Hermitian. So also the right hand side is 0, that means An minus Am star Mn. Okay, we already know that eigenvalues are real. So Am star can be taken as Am. So An minus Am, Mn equal to 0. Of course, M not equal to N. If M you take it equal to N, then obviously you get the result here, M is 1 and Am minus Am star equal to 0. That means it gives trivially the same proof that Am is equal to Am star, that means the eigenvalue is real, but that we have already accepted and proved. So the natural case is M not equal to N and the product of these two things is 0, and that can be because of either of them is 0. Now Mn and Mn are not same, that means you have taken two different states, eigenstates or eigenfunctions, right? But two different eigenstates may have the same eigenvalue or different eigenvalues, right? If they are same eigenvalues, that means degenerate, then An and Am are same, so this part is 0. But if they are not same, that means M not equal to N, and not only that, An is not equal to Am, that means the states are different and their eigenvalues are also different, non-degenerate case. In that case, this part is not equal to 0, then obviously this part is 0 to make the product to be 0. So Mn is 0. That means this psi m and psi n are orthogonal. So what we see and what we have proved, that if operator A is Hermitian, then their non-degenerate eigenstates are orthogonal to each other. Okay. But the question then, what about degenerate? If Am and An are same, then it cannot give a guarantee that Mn is 0. But we have seen that it can be seen that even in that case the functions can be made to be orthogonal. Okay. There are some methods like Smith orthogonalization method, but that we are not discussing today here. Well, an interesting catchy line, if I are not there, quantum mechanics would have been impossible. So at the first glance, it refers that I is someone, some scientist, some physicist, without whom quantum mechanics would have been impossible. But I am not really talking about any physicist. Rather, okay, let us see in a different way. Suppose we start with an operator ddx. A is ddx. Okay. Now, can we check that A is Hermitian or not? Yes, of course. We have to see the equality of these two. So turnover rule. So F star operator F, and now F comes here and F star goes there. So F ddx of F star. These two have to be same, but it can be shown by integration by parts that actually they are not same. Rather, it can be shown that this is equal to minus of this, where the demand was without the minus, if ddx is a Hermitian operator. So what we see here, that ddx is not a Hermitian operator. Okay, but I will make you, that means operator A, Hermitian. So as if someone is saying that okay, you are not, but I will make you Hermitian. So who is that person? It's not a person. Is I here is root over minus 1, right? That means we are talking about a different operator, which you know, that momentum operator. ddx is not a Hermitian, but if I multiply by minus ih bar, then it is an Hermitian operator. It can be shown. It can be shown in the sense that in that case F star, again turnover rule, P F. Now F comes here and F star goes there. That means F P star F star. If these two are same, then P is Hermitian, and it can be shown that yes, they are same and they are equal to this quantity. By integration by parts, it can be shown. So ddx is not a Hermitian, but after multiplication by I or minus I h bar, the whole thing becomes Hermitian. So I makes the operator ddx to be a Hermitian. So I will make you Hermitian. Actually, I mix Hermitian. Okay. That's a home task that you can show that by same way that kinetic energy operator is also a Hermitian operator. Well, a few questions. Under what condition CFBG is equal to FBCG? Okay. So let us see. Right hand side FBCG. Now BCG, it is equal to BCG, provided B is linear. That is the property of linear operator. And then what next? Now C is a constant, so it can come out of integration. So C FBG, FBG. This is the right hand side. Now what about the left hand side? CFBG. Now C is in the bra position. So if you want to take it, it's a constant, but in the bra position. So if you take it out, you have to take it as C star, complex conjugate of C, right? So what we see, that the right hand side and left hand side, if they have to be same, then C has to be equal to C star. So my final answer is, first of all, B has to be linear, and then C is equal to C star. If it is so, then this equality holds true. Okay. Next question. What operator is shown to be Hermitian by the equation Fg equal to Gf star? So it seems that nothing is there, but actually the answer is an operator is there, which is multiplication by 1. It's a rather trivial and tricky question. The next one is a square average is it's not really average. A square, okay, you can call it average. Is it equal to SI if A is Hermitian? Yes. Why? Because if you just apply that A square average is psi A square psi by definition. Now if A is Hermitian, then as I have suggested, that you can take the thumb rule that the operator comes from here middle to the left. So you get A psi and then Si. So that is given in the question. So it's a one line answer that if A is Hermitian, that we can write in this way. Fine. Next question, kinetic energy average Tx is half m psi px squared psi by definition. But then you have to show that this can be written as this d psi x and here h bar square by 2m. So can we? Yes, it's a question from Levine. Now Tx average is p square by 2m average, that means psi px square psi and px square, so 1 px comes here by turnover rule because px is Hermitian. So px psi. Now px is h bar ih bar ddx, right? So from this bra ih bar minus ih bar, but in bra position. So from this px psi bra position px psi, it gives you ih bar and the ket px psi gives minus ih bar, right? And then d psi dx. So this ih bar and minus ih bar gives you h bar square. So what we get? H bar square by 2m d psi x. So that is exactly wanted in the question. So proved. And the next question is a related question that Tx is given like this in the earlier question. Then you have to show that T average is greater than or equal to 0. So again it's a question from Levine. Now dx psi and dx psi, this quantity can never be negative, right? So from the question itself, Tx average is greater than or equal to 0. And similarly Ty and Tz, and T is a sum of all three, Tx average, Ty average and Tz average, and all three for each of them is greater than or equal to 0. So obviously T average greater than or equal to 0. Okay. If A and B are Hermitian, then under what condition the product AB is Hermitian? Okay. So if we just use the turnover rule, the thumb rule, it can be easy to show. The first of all answer is yes, only if A and B commute. So if A and B commute and they are Hermitian, then their product AB is also Hermitian. So let us try to prove it. Now psi AB psi, the starting point. Now A and B are Hermitian. So as I mentioned that A you can take it from middle to the left here. So A psi and then B psi because A is Hermitian. Now since B also is Hermitian, so you can take now B to left here. So it gives you BA psi psi. Okay. So from one side we get BA psi psi. Now the product AB, if this product is to be Hermitian, then the condition is that psi AB. So the product AB as a whole it's Hermitian, that means we can take it by my thumb rule from middle to the left. So AB comes here as such psi psi, right? So psi AB psi, that means the red colored BA psi psi should be equal to the green colored AB psi psi, right? So what we see that BA psi psi should be equal to AB psi psi. That means BA must be equal to AB. So that means they commute. They have to commute. Okay. I think you have got the point. Now the question in continuation to the earlier one, that if the product XPX Hermitian? No. Why? Because in the earlier problem we have seen that the product is Hermitian if they commute, but we know that X and Px they do not commute. So the product XPX is not Hermitian. Okay. The next one, if A and B are Hermitian, then is their anti-commutator also Hermitian? Now you know anti-commutator is AB plus BA, where commutator is AB minus BA and anti-commutator is AB plus BA. So the question here that whether AB plus BA Hermitian or not, if A and B are Hermitian. The answer is yes, they are Hermitian. How? Again the same trick, that psi AB plus BA psi. So you can write psi AB psi and then psi BA psi, psi AB psi and psi BA psi. Now the same trick, that AB, so first you take A to left and then B, both are Hermitian, then B, so you get actually BA psi here, and in the second part first you bring B to left and then A to left further, so AB psi, so you get here AB psi. Okay. Now you take common BA and AB to get psi psi, so BA plus AB psi psi. Okay. So AB plus BA, the whole thing as such comes to the left and is equal, so BA plus AB comes here. Okay. So that means the whole thing, that is BA plus AB, is Hermitian. That means the anti-commutator is also Hermitian if A and B are Hermitian. Okay. The next question, whether half xpx plus pxx Hermitian? Obviously the answer is yes, because x, px, each of them is Hermitian and it's nothing but anti-commutator. So just we have proved in the earlier problem that the anti-commutator is also Hermitian if x and px individually are Hermitian. Okay. What do you mean by A is anti-Hermitian? So we have seen so far anti-commutator, but here anti-Hermitian. So anti-Hermitian, FAG turn over GAF with star, it's the definition of Hermitian, but if you put a minus sign then it gives you the anti-Hermitian. So FAG is minus GAF whole star, or the same trick that you bring A towards left, so minus AFG. That is the definition of anti-Hermitian. Well, if A and B are Hermitian, then is their commutator AB minus BA anti-Hermitian? If A and B are Hermitian, then is their commutator AB minus BA anti-Hermitian? Yes, quickly check that AB minus BA, start with that, and that is psi AB psi minus psi BA psi. Now the same trick, you first bring A towards left and then B, so you get BA psi psi, and here first B then A, so AB psi psi. Okay. Now if you take minus common, so AB minus BA psi psi, AB minus BA psi psi. So the AB minus BA whole thing as such, as if you can take it towards left, but with a minus sign. So it is the anti-Hermitian, because that is the definition, with a minus sign. Okay. So the point is proved. Thanks for watching. Next video, session 16, it will be coming soon, and it will be actually the part 4 of quantum concept booster. The fourth part would be true false kind of session, and I have a plan of having more than one session with true false type questions. So it will be part 1 of true false in quantum, part 4, session 16. So thanks for watching again. Please keep on watching, do subscribe and encourage your friends to subscribe. Thank you very much.